Hello, this is Teresa Stack. I'm an associate professor for Montana Tech, and this learning unit will cover flammable liquids and also review some information on flammable gases. It follows the OSHA standard quite closely, which is 29 CFR 1910.106, flammable liquids. So the two primary hazards associated with flammable liquids is explosion and fire. So you can see both fire and explosion. And this is a University of Lyon in France. So what you are watching is a video of a gentleman who is near a fracking operation, and when he turns on his faucet, the benzene, along with other flammable vapors, is insoluble in water and is carried with the water. Once again showing you that it is the vapors that burn and not the liquid. Flammable liquids are divided into 4 categories by OSHA. And again, it's the combination of the flash point and the boiling point. The lower the number, the more volatile the flammable liquid. The easier it is to catch fire and potentially have an explosion. So our first category, category 1, is a flammable liquid that has a flash point of less than 73 degrees and a boiling point of less than 95 degrees. So this could be, room temperature and being outside when you think about 73 degrees and 95 degrees. A category 2 flammable liquid has a boiling point of greater than 95 degrees, but a flash point of below 73 degrees. A category 3 flammable liquid has a flash point between 73 and 140 degrees Fahrenheit, and a flammable 4 category liquid has a flash point between 140 and 199.4 degrees Fahrenheit. So this is a general rule for storing flammable and combustible liquids. It's okay to store those together. You need to segregate them from most other hazard classes and completely isolate them from organic peroxides, which, as you can see, organic peroxides need to be isolated from all of our categories of hazardous materials. And our categories listed here are related to Department of Transportation. Even though we're talking about OSHA, sometimes these rules overlap. So the Department of Transportation regulates flammable liquids under 49 CFR 173.120. OSHA regulates them under 29 CFR 1910.106, as well as Subpart H under hazardous materials. And so some specific areas under flammable liquids are spray finish using flammable and combustible materials, dip tanks containing flammable and combustible liquids, and additional requirements for dipping and coating operations that use flammable or combustible liquids. So you have the use of them in large quantities as well as the storage of them in smaller quantities. So the rules are segregated by industry. So I'm showing you an example, a Navy example of where this is a dip tank operation, and they were working with a flammable liquid. And you can see that the worker is leaning inside of the dip tank, and he would have to rotate that part around. And the first stage in the dipping process removes the grease from the outside of the engine casing, and that's what you're looking at here, some type of engine part. And he would also use that long stick that you could see in the foreground to be able to rotate the part. And he is wearing appropriate personal protective equipment for that. although the gloves look a little short in this particular picture, although I can't judge his PPE. So also covered under the OSHA rule is spray finishing with flammable material. And this is a thermal flame spray process where you deposit molten and semi-molten particles onto the surface. And again, this is a Navy operation, and they were covering these watertight doors. And that the particles travel at high velocity and they flatten on the surface, providing a nice coating or sealing, so it seals it together. And these flattened particles are known as splats, and they build up along the outside of the surface. And this is done before you would take a product like this and then put it in a paint booth, like to powder coat it. So you would do this first before you powder coat it. And this is another example of where flammable materials would apply. So you could see, like right here, oops, the wire, here's the wire, and it's being fed into the gun that the worker is holding in his hand. And we wanted to actually, this was part of an ergonomic solution, we wanted to put a solution in place, and this was the solution, would be to have this flame spray on a gimbal that would rotate so that they wouldn't have to hold the flame spray gun in their hand because it was quite heavy. But I'm just going to show you another example of what flame spray looks like. So he's lighting the pistol and starting the feed. He's feeding this wire that you could see right here through the flame, and it gets really hot. I think it's like 3,500 degrees. And he just goes through and he is melting that flammable solid and providing a coating on top of the product. So there was a lot of resistance when they were feeding the wire through, and that's why they would have it up over their shoulder. And that was the harder thing to fix as far as using this ergonomic solution, was how to get that wire to feed through, because that rate in which it was fed is important if you need to lay down the material at a certain thickness. So we did cover this with the properties of hazardous materials, and we went through our chemistry. But remember, all flammable liquids have a lower and an upper explosive limit, or flammability range, and that's the difference between the upper and the lower. And that there's a point where a mixture is too lean, where it is combustible, and where it is too rich. And this actually brings us forward into 10% of the lower explosive limit, and we start to look at a good time to review kind of our confined space standards. But first, let's take a look at gasoline. And in this example, he's using a sparker, and he puts the sparker really close to the gasoline, and this is too rich. There's too much vapor. The gasoline will not burn. And then he moves his hand up and he moves further away, and here the mixture is too lean. There's not enough gasoline vapor for the gasoline to burn. And then he hits that combustible range, and the gasoline burns the vapor again right down to the top of the mixture. Okay, so we moved from flammable liquids to a quick review of confined spaces, which is found under 29 CFR 1910.146. And that is just because of this principle of the lower explosive limit and have to doing atmospheric monitoring inside of confined spaces. And we want to bring all this material together to make a useful package of information for us. So a confined space has a limited or restricted means for entry or exit. It is not designed for continuous occupancy. Not all confined spaces are permit required confined spaces. So you may have a space that is considered a confined space, but it may not be a permit required confined space. A permit required confined space meets one or more of these criteria plus has limited or restricted means of entry or exit. So it contains or has the potential to contain a hazardous atmosphere. It has an internal configuration such that the person who is entering could become trapped or asphyxiated by inwardly converging walls or floors which slope downward or taper into a smaller cross section. So think about a V upside down, or being like in a silo where if you fell in you wouldn't be able to get out, or a liquid vat. Or contains materials that has the potential to engulf the entrant, and the entrant is the person who makes entry into a confined space, and these are specific terms used by OSHA. So some examples of confined spaces, whether they're permit required or not, means that they meet one or more of those previously defined terms. So silos, pits, vaults, tanks, and hoppers, as well as crawl spaces, can be seen as confined space. So if you have an elevated entry portal, it's a permit required confined space when the entry portal or opening is 4 feet or more above grade. And this usually requires some knowledge of high angle rescue because of the difficulty of getting somebody out of a space or a portal that is at 4 feet. So it is, at my head level or higher. As well as another definition of a permit required confined space is when the means of entry is lower than 4 feet below grade. And this would, of course, require some form of rescue team, and usually you have a tripod in place to perform the rescue. So we could see our below grade picture here, where potentially, depending on how high this opening was above the ground, that may be an example of an elevated entry. So if you have a restricted portal, it is a permit required confined space, and that is less than 24 inches. And this is too small to allow the rescuer to enter wearing a self-contained breathing apparatus. So in this example here, if you have a restricted entry area and you're wearing a breathing mask, like think of a scuba mask, but instead of going underwater, you're out of the water. Sometimes you have to take your tank off and push it in front of you, and that would be an area where it had restricted access. Unrestricted access is greater than 24 inches. These portals allow relatively free movement into and out of the permitted space. So the portal size restricted versus unrestricted. So if it's restricted, it's a permit required confined space. So the standard also talks about periodic monitoring in atmospheres, and to monitor the whole layers within the container, because atmospheres will stratify or separate. And also atmospheric conditions can change when people are in confined space, especially if they're doing work or you have a mixing effect. So the gases when you're in a confined space could be mixed around, right? Because you're in that space together. So what is a hazardous atmosphere? An atmosphere that may expose employees to the risk of death, incapacitation, impairment of ability to self-rescue, acute illness, and that could be caused by one of the following. So that's flammable gases, vapors, or mists in excess of 10% of the lower flammability or the lower explosive limit, as well as oxygen deficient or oxygen rich atmospheres. So an oxygen deficient atmosphere is below 19.5% oxygen, and an oxygen rich atmosphere is above 23.5% oxygen. So we're monitoring for 10% of the lower flammability limit, and this is the lowest concentration of gas and air mixture that will ignite by volume. We calibrate our meter, which reads this lower flammability limit to a specific gas. So we may calibrate it to methane, which would be 500 parts per million. We may calibrate it to isobutylene at 180 parts per million, or gasoline to 120 parts per million. So we're calibrating it to 10% of the lower limit of a very specific gas. And our meter is a dumb meter, and it's only going to read what we calibrate it to. Please, again, remember, don't confuse toxicity with lower explosive limit. So if we were calibrating our meter to benzene, this is the NIOSH Pocket Guide cut sheet for benzene, we would set our alarm to go off at 10% of the lower flammability rating of benzene, which is 1,200 parts per million. And you can see here that we would be dead before we would blow up with benzene. Don't confuse toxicity with flammability. And here you can see a website of some of the lower and upper explosive limits or flammability limits. Remember, these terms are used interchangeably of some common gases. So when we test our atmospheres, when somebody is entering a confined space, we need to make sure we test all of the different layers, because good air could be on the top and deadly air can be on the bottom, or of course this mixing effect could occur. There are some gases, hydrogen sulfide, ammonia, methane, esters, carbon monoxide, sulfur dioxide, and nitrogen oxides that tend to go to the bottom. They're typically caused by improper disposal of petroleum products such as gasoline and mineral spirits, and they contribute to something that we call sewer gases. A lot of times when we have a 4-gas meter, we'll meter for lower flammability of isobutylene because it has such a low limit that it alarms before other things will alarm. We register for oxygen, and then we register for hydrogen sulfide, H2S, and this allows us to measure for multiple gases. And sometimes they call these sewer gases. They have the potential to cause fire and explosion. So here's, we're going back, we're leaving this area of talking about confined spaces and the lower explosive limit, and we're going back once again to flammable liquids. Flammable liquids can cause fire and explosion, and like many other substances, may have health effects. On the NFPA label or diamond, a rating of 3 or 4 means that the liquid is a flammable liquid. And these are our 4 categories that are assigned by OSHA. Remember, for the first 2, it's a combination of the boiling point and the flash point, 1 being more highly volatile than 2, and 4 being way less volatile than 1. So although we're talking about flash point and boiling point, you need to have all these items in place for a fire to sustain. You need the fuel, the oxygen, and a chemical reaction, as well as the spark or the heat source or the source of ignition. And this can be anything from open flames, smoking, static electricity, cutting and welding operations, working on hot surfaces, electrical or mechanical sparks, as well as lightning. Can't stress enough that a flammable liquid will generate its own static electricity when it's sloshing around in a tank or being transferred into a pipe. It's because the electrons are lining up. And it's very important to ground and bond material when you're transferring flammable liquids. I think I'll get some gasoline. It might not be too cold since I'm not wearing a heavy coat, but cold enough that I'm wearing a sweater. And I just slid out of my car and maybe built up a little static electricity. And then I get back in my car. I do not touch my car. I wait in my car for a little while. Get back out of my car and back in my car. Again, I don't touch my car to discharge that static electricity. Messing with my sweater a little bit, and it's enough of a spark, given the vapor pressure of the gasoline, the vapors, to cause a fire. Well, just a flash. I think that video really displays the effects of static electricity and how small of a spark is required to create a flash, where if you had enough fuel source, it could create a fire. So to eliminate the difference in static potential between 2 objects, we bond them and ground them. Bonding is when you link object to object, so 2 tanks together, maybe the tanker truck to the wall. This would be bonded. And grounded is where then you link the item that is transferring the liquid out to the ground. And this will eliminate the difference between object to object static electricity and object to ground static electricity, because of what happens when you transfer flammable liquids. They build up their own static electricity on their own. And so here's an example of a tanker truck. And in many of the pictures that you posted on the website for Hazardous Materials Around Us, there were tanker trucks that were offloading, and you can see them grounded and bonded. So we're going to move on now and talk about storage of flammable liquids in not big storage containers like you see here, so not crude oil, but in containers that are small portable containers. And so by portable containers, that's under 660 gallons. And so there's different rules for 0 to 60 and different rules for 60 to 660, as well as all the different categories together. So allowable containers based on classification of flammable liquid. You can see approved tanks, metal drums, safety cans, glass containers, and the different categories 1 through 4, 4 being the least volatile of all of the flammable liquids. And again, portable is less than 660 gallons. So stationary tanks, not portable tanks. Stationary tanks are made of steel or other non-flammable material, and they must have emergency venting to prevent a vacuum or rupturing, and they should be contained within a secondary containment area or dike to hold the full capacity of the liquid. So let's watch what happens when you don't properly vent a storage tank. Safety cans are recommended for the storage of flammable liquids. They're approved containers for not more than 5 gallons. They have a lid that automatically snaps shut in case it starts to flash, and a safety valve that would relieve pressure in case pressure started to build up inside. And you can also see it has the transfer on the bottom so that you don't have the vapors that build up when you're using a bottom feed, as opposed to running along a hose, and then not that the vapors would build up, but you can have a buildup of static electricity that way. And they're supposed to have also, what safety cans contain is a flame resistant screen, which increases the surface area inside and creates a rapid dissipation of heat in case you did get a flash. So the top would automatically snap down, and then the heat would dissipate so that the can itself wouldn't explode or catch on fire.